Okay, hello everybody. My name is Sakari Palasturo. I come from the University of Oulu, Finland. And today I'm going to introduce the studies what we have been doing during my visit at NTNU in Norway on the lab of Professor Chien Chang. So the topic is hydrogen embrittlement at low temperatures in ultra-high strength steels. So, I'm going to introduce the motivation for this research, go through the experiments and modeling, show some results, and then end up in conclusions. And since time is limited, I try to adopt the KISS principle so we can discuss the technicalities after the presentation. So, the question is, do we have hydrogen embrittlement at low temperatures? Because given the literature, we don't know much about it. We have a huge concentration of research and room temperature properties, but not too much in sub-zero. So we are to study the effects of hydrogen in fracture toughness and in impact toughness tests at sub-zero temperature. So standard tests, and the driving motivation for this research is the ultra-high strength steels request for Arctic applications and, well, better toughness properties. And the known literature references. And yeah, I can also challenge you to show some papers from that area because we didn't find. So the literature is very limited to temperatures above zero, slow strength rates, and mostly tensile tests. But what we do know that the higher the strength level, of course, the more prone they are to hydrogen. So if we take, for example, the solubility of hydrogen to pure VCC ferrite, which is around 0.7, we see that we can quite easily run into problems with these steels. So our target was test the susceptibility of Aspen's microstructures to hydrogen embrittlement at the tactile brittle transition temperature region to determine the degree of plastic deformation and to model and verify this cohesive zone method to these circumstances. And our simple hypotheses are that hydrogen content plays a role even in these circumstances, that there's a loading rate difference between impact toughness tests and relatively much slower fracture toughness tests. I made two different microstructures from S960QL steel plates. First, a single-phase Aspen's martensite, some here, and mixed-phase Aspen's martensite and bainite. And the essential difference between these two is the precipitation morphology and where they are in the microstructure. As you see, the yield strength of these steels is around 1000 megapascals. They have sufficient ductility and quite high hardness. And these are used in this condition in weight critical applications, like mobile equipment and so. So, simple flow through of experiments, charging, testing, and analysis. We used passive catalytic protection in a seawater-like electrolyte to produce more hydrogen into these steels with a charging time of roughly 4 days. Then we did fracture toughness tests with 3-point bending specimens in cooled alcohol. With a displacement rate of 0.5 millimeters per minute. So we did the standard of ASTM in 1921. And then instrumented SharpUV impact toughness tests. And the test temperatures used here were -20 and -40 degrees Celsius. We used melt extraction to define the total hydrogen contents in uncharged and hydrogen charged conditions. And the results where we have two distinctive levels in both microstructures. Fractography to identify the hydrogen embrittlement related features. Then kernel orientation method to measure the degree of lattice deformation or distortion. And cohesive zone modeling to test its applicability to these conditions and to model and expand these tests even further. So kernel average misorientation is this EBSD-based technique of measuring local variations in lattice orientation. So it compares very local, intra-grain data points with their neighboring points, and thus it creates a pattern difference map. So here we have two examples from literature that we see that the deformation is concentrated around the propagated track, and here we have another example of formed Osnard lens in a ferrite matrix, and due to this volumetric expansion it causes deformation in the interface of ferrite matrix. And then cohesive zone modeling, it's a technique that models the traction process zone ahead of the track tip. And it's implemented in conventional continuum model by inserting these cohesive elements on the anticipated track path. And the behavior of these elements can be described by this traction separation law, which constitutes of cohesive critical strength at the maximum level of the critical separation, and the damage accumulated is accumulated under the curve. And how we implement hydrogen embrittlement to this study is that we expect that hydrogen reduces the maximum cohesive strength needed for the separation of these cohesive interfaces, or in this case, the cohesive elements. That, of course, corresponds to hydrogen enhanced cohesion. And it's done in this three-step procedure developed by Vicky Sullivan and others. So first we do elastic stress analysis to get the hydrostatic stress state. Then mass diffusion analysis to calculate the local hydrogen contents in these stressed areas. And on the third step, the cohesive step with the cohesive elements, hydrogen-informed cohesive elements. So we use the traction separation law of Needleman with the added viscosity term of Gall and Bauer to handle these convergence problems what we can run into when the separation of these cohesive elements. And the hydrogen degradation law, which describes how much the cohesive strength lowers as a function of hydrogen, is used this quite recent law of Yu et al. So, results. In both fracture toughness and impact toughness tests, we get a decrease in toughness values in both temperatures, and both decreases are significant. And also the mixed phase microstructure was bigger than this single phase Martensite, but further research will be done on those different microstructural properties later. And fractography shows essentially a combination of brittle fracture with the ductile band separating brittle areas, so very normal to this transition temperature region behavior. But we are also able to identify hydrogen embrittlement related features throughout the fracture surfaces. So we have classic cleavage, flat features, and also local intergranular fractures. So here we have these lat-like or lat-sized features on these flat areas, and then in this example we have a cleavage fracture propagated that is indicated in this local intergranular fraction. So, well, never mind. Kernel average misorientation measurements, they show the deformation under the fracture surface, so it's highlighted in this more red area under the surface. And what we can see from here that with lower hydrogen content, we have higher degrees of lattice distortion, which is highlighted in these areas. So more hydrogen, less plastic deformation. Cohesive zone modeling results. The essential thing here in this first case, it's really dropped down, but never mind, is the distance of this green dot to this gray dot. So due to the successful calibration, we get a very good agreement in the model with our experimental tests. And when we insert more hydrogen into the model, we actually expect even higher degrees in toughness values than what observed in our experimental tests. And we also enhanced the diffusion rate to model slower displacement rates. And then we see even a further additional decrease in toughness, so from this point to here, and from here to here, and that it can be explained by the findings that the hydrogen population is more in line with the hydrostatic stress state with a sufficient time for it to accumulate there in larger quantities. Then, if this works, can you click on it? Yes, well, slow video which just shows that the does it go around? Never mind. It shows the separated elements. So we took the failure point as the complete separation of the second element in our model, which corresponds to the fracture propagation before the brittle fracture in the specimens. So conclusions are that yes, we do have hydrogen embrittlement present also at sub-zero temperatures, and that is backed by our findings of decrease in fracture toughness and impact toughness values. Our fracture surfaces show hydrogen-related features, and we get a lower measured elasticity with higher hydrogen content. And we have also constructed and verified this hydrogen-informed cohesive submodeling for these low temperatures and relatively fast strain rates, and it gives good prediction of our toughness properties in the experiments. So attempt is made to start to cover this region, but still I'd say that there's a lot to do to get better understanding of the properties at low temperatures. And it's also good to keep in mind that the same hydrogen contents what we had in these past tests would most likely be fatal at higher temperatures in real-life service times and in highly stressed features. So with that, I want to acknowledge my funding partners and collaborators and say thank you.